And the first thing we have to do is to introduce something called the highest occupied energy level or lowest unoccupied energy levels. In chemistry, and I don't know if you have worked with molecular orbitals yet, we would normally refer to these energy levels as highest occupied molecular orbital, HOMO, and lowest unoccupied molecular orbital called LUMO. But it's the highest energy level that has electrons in it, and the lowest unoccupied energy level is the energy level that the first one that is unoccupied, doesn't have any electrons in it. And then we can have to be able to count conjugated bonds and how we can define and relate energy to a wavelength using the definition of a photon. And then we look at complementary colors. And if you just remember, that is that the visible spectrum, so colors, have wavelengths from 400 to about 800. If we have lower, so higher wave numbers, which means lower energies, it's above 800. And if it has very short wavelengths, as we saw from the particle in the box, the shorter wavelength, the higher energy, we are in the UV-VIS part of the spectra. So I'm going to introduce EFIN to you, because I don't know if you have been working with conjugated bonds yet. So this is, but I do believe you have. So this is just a reminder. If I have EFIN, each of that carbon here will have the carbon that have an interaction, which is a double bond. Each of those carbons has 1 electron in its pi electrons. So each carbon has 1 electron. So that means we have 2 electrons. If I was going to put those 2 electrons, I would have 1 carbon bond. So I would be in the lowest quantum number, n equals 1. That means that these 2 electrons would be in my highest occupied molecular orbital, or the highest occupied energy level. That is my HOMO. And what I can do is that I can excite one of these electrons from my HOMO to my LUMO. That is called my excitation energy. And the energy difference between the HOMO and the LUMO is given by this equation here, which I have derived from this the energy that I specified for this individual energy level. So I've taken the difference of the one with n equals 1 and the n equals 2, and I have derived this equation. And as part of the post-lecture exercise is to actually show that this equation is correct. So what does it mean that I excite an electron from HOMO to LUMO? If I would take beta-carotene, beta-carotene is a longer conjugated chain, longer than the EFIN that we saw before. And we know that carrots are orange. And the color of this carotene depends on the length of this conjugated chain. I use that as my box. So that is the L in my box. So I can then identify the length of beta carotene. So now I have a length of the box. Can I now calculate this energy from this equation? Let's see if we can do that. First of all, we need to calculate how many conjugated bonds we have. Because we have 1, 2, 3, 4, 22 carbons in this conjugated bond, we have 22 electrons. Just like for EFIN, we had 2 because we had 2 carbons that was double bonded. If you remember what we did here, we always put 2 electrons in each energy level. So I do the same here. if I put 2 energies in each energy level, I can only have max 2 electrons in each energy level. I have 11 energy levels occupied. So my HOMO will be n equals 11, and my LUMO would be n equals 12. So then I have my n, which is my 11, because that corresponds to the highest occupied energy level. And I can now look up what this H is, and that is called Planck's constant, and I'm sure you have heard about it. It's 6.626 in the power of minus 34 joules per second, and the units are important. Always remember your units. I can now calculate the length of this chain if I know the length of single bonds and double bonds. And if I calculate the bonds lengths of this, or the length of this chain, it's about 30 in the power of minus 10 meters. So 30 angstrom long. And then I have the m, which is the mass of the electron. And if I put in these numbers, I get a value that is 1.51 in the power of minus 19 joules. So I have the numbers and I put them in. That should have been a 1. I do apologize. It's 1.51 in the power of minus 19 joules. I check my units. Planck's constant is joules per second. And then I have c, which is the speed of light, which is in meter per second. My joules and joules are cancelling out. My second and second are cancelling out. So what I get is that I have a wavelength and it's given in meters. So now I have a wavelength, a number that is 3.06 in the power of minus 6 meters, which is 1.306 nanometers. So beta carotene absorb light with a wavelength of 1,306 nanometers. So I excite an electron when I absorb the energy. So what I'm doing is that I have my HOMO and I excite it to the LUMO, like it was coming up in this little cartoon before. Sorry. So the message to take away is that I have a conjugated polymer which allow me to calculate the length of a box. We have 2 equations that I expect you to remember and to use. And that means that I can calculate and derive a wavelength from the energy, which depends on this energy difference between the HOMO and LUMO. So what does it mean? So what is the color of carrot then? So I have my HOMO, and by shining light on it, what is going to happen when I shine light on it, all the different colors are going to hit my sample. And I excite 1 electron from the HOMO to the LUMO. And when I do that, I will absorb 1 wavelength. That wavelength, if it is the blue one, it will not come out of the spectra anymore. We will not see it. And it's the blue color that is absorbed. That means that what we are going to see is the complementary color of the carrot. So it is an orange color. That is what we expect, at least. But if we take this wavelength that we calculated, 1,360, it's here. It's in the IR region. So actually, the carotene we have calculated, we would see as UV-VIS, which means we wouldn't see it. Actually, the carrot would be out sunbathing. So it's not exactly correct using the particle in the box, but it is not completely incorrect either. We are in the right region using this approximation, and that is a good thing. So what we can do to prove that it is blue is that we can put our carotene in a UV-VIS, which is a piece of equipment. We see which of these colors that is absorbed. And if I follow carotene, which is this orange line, I will see that I have a peak at about 497 nanometer. And that corresponds to the blue light. And that means that the blue light is absorbed, and I will see carrots as orange. And that is because what we will see is the complementary color. So if we absorb blue, we see the complementary color, which is orange.